So let the set G, together with some notion of multiplication, be a multiplicative magma if the underlying set does not contain the multiplicative identity. Then the magma fails to be a monoid and therefore also fails to be a group. Now, if the underlying set contains the additive identity, then the magma fails to be a group, since the additive identity has no multiplicative inverse. Now, in the first lecture, we first talked about a deleted set, and at that time we defined it to be those non-zero elements in the set. Now, sometimes the non-zero elements in a set do form a group under multiplication, but not always, as we will see in the case of the integers. And so we now need a more encompassing definition for a deleted set. And so we will now define it this way. The deleted set from the set G is a set of those elements in the set G such that the multiplicative inverse is also in the set G. So in other words, we have removed or deleted those elements in the set that do not have a multiplicative inverse. So next, we will show that the non-zero integers under multiplication is a monoid, but is not a group. Okay, so proof. Let A and B be in the set of non-zero integers. Then A and B are integers such that A is not equal to 0 and B is not equal to 0. And so the product, A times B, is not equal to 0, since the integers under multiplication has no zero divisors. That is, the product, A times B, is in the set of non-zero integers. And so the non-zero integers under multiplication is a magma. Now let the elements A, B, and C be in the set of non-zero integers. Then, since this set is a subset of the entire set of integers, the elements A, B, and C are in the set of integers. And so the product, A times the quantity, B times C, is equal to the quantity, A times B times C, since multiplication is associative. Over the integers. And so the structure consisting of the non-zero integers under multiplication is a semigroup. Now there does exist the multiplicative identity in the non-zero integers, such that for every other non-zero integer, a times 1 is equal to 1 times a, which is a. And so the non-zero integers under multiplication is a monoid. Now notice that 1 over a is in the set of non-zero integers only for the case a equals 1. And so the non-zero integers under multiplication is not a group, since it is not true that every element has a multiplicative inverse. So the linear equation a times x equals b, where a and b are integers, has a solution in the set of integers if and only if a divides b. So as the integers under multiplication is not a group, we are not guaranteed that every linear equation with integer coefficients has a solution or has a unique solution. We indeed only have a solution in the set of integers if a divides b. So as a special case, the equation a times x equals 0, where a is a non-zero integer, has the solution x equals 0, since the integers under multiplication has no zero divisors. But recall that in order to prove that the integers under multiplication has no zero divisors, we had to solve the equation ax equals 0, not in the set of integers, but we had to allow for the indeterminate x to be in the set of rational numbers. So next, we will show that the integers modulo n under addition modulo n is an abelian group. So proof, we have already demonstrated that the integers modulo n under addition modulo n is a monoid. Now for every non-zero element in the set of integers modulo n, there exists an additive inverse, namely n minus a in the set of integers modulo n, such that a plus n minus a is the same as n minus a plus a, which is 0. Further, 0 plus 0 is 0, so 0 is its own additive inverse. And hence, the integers modulo n under addition modulo n is a group. Now for every two elements in the set of integers modulo n, it does not matter the order in which we perform the sum, we always obtain the same result. And thus the structure consisting of the integers modulo n under addition modulo n is a Boolean. So we can now show that the nth roots of unity under multiplication is an abelian group. So proof, as the integers modulo n under addition modulo n is an abelian group. And the integers modulo n is isomorphic to the nth roots of unity. The nth roots of unity under multiplication is an abelian group. Okay, so let's return now to the factored quadratic x minus 1 times x plus 1 equals 0, and we're going to solve this equation in the integers. Now, as there are no zero divisors in the integers under multiplication, the fact that the product of two factors equals 0 means that at least one of those terms or those factors must be equal to 0. And now we have linear equations in the group of integers under addition. And so we are guaranteed a unique solution for each of the equations. And so we can proceed to solve these equations. And once again, we find that the solution set is -1 and 1. So now let's revisit the integers modulo 4 under multiplication modulo 4. And let's quickly construct the multiplication table. The elements in this set are 0, 1, 2, and 3. Zero times any element is 0. 1 times any element is that other element. Now 2 times 2 modulo 4 is 0. And 2 times 3 modulo 4 is 2. And 3 times 3 modulo 4 is 1. So again, the number 2 is a zero divisor since 2 times 2 is 0. Notice that this is the only zero divisor in the set of integers modulo 4. Also notice that the numbers 1 and 3 have multiplicative inverses. In fact, they are their own multiplicative inverses, since 1 times 1 is 1 and 3 times 3 is 1. And so if we solve the equation, x minus 1 times x plus 1 equals 0 in the set of integers modulo 4, then this equation is true if both factors are equal to 2, or if either factor is equal to 0. Now we have linear equations in the group of integers modulo 4 under addition modulo 4, and so each linear equation has a unique solution in the set of integers modulo 4. And so if we now proceed to solve, we have x equals 3, x equals 1, x equals 1, x equals 3. But notice that overall, the factor x minus 1 leads to two solutions, 3 and 1. Likewise, the factor x plus 1 leads to two solutions, 1 and 3. So the solution set is 1 and 3, but as the integers modulo 4 under multiplication modulo 4 is not a group, we are not guaranteed a unique solution for the product. But once we reduce it to linear equations in the group of integers modulo 4 under addition modulo 4, we are then guaranteed a unique solution for each linear equation. But once again, not a unique solution for the product. So if we now form the deleted set of integers modulo 4, that is the set of those elements in the integers modulo 4 that have inverses, then this is the set which contains 1 and 3. And so if we form the multiplication table, 1 times 1 is 1, 1 times 3 is 3, and 3 times 3 is 1. So this structure is closed under multiplication. There are only two elements in the set, but if we multiply 3 in any combination, any way that we group them, then we obtain the same result. So we have a semigroup. The number 1 is the multiplicative identity, and it is in the set. And 1 is its own inverse, while 3 is its own inverse. So this structure consisting of the integers modulo 4, the deleted set of integers modulo 4, under multiplication modulo 4, is a group. And so, for instance, we have a solution. We are guaranteed a solution to the equation 3 times x equals 1. And if we look at the multiplication table, we see that the solution is 3. So finally, notice that the deleted set of integers, that is the set of those elements in the integers that has a multiplicative inverse, is a singleton set which contains the number 1. And that the singleton set containing 1 under multiplication is a group. And this is an example of the trivial group. And we'll look at the trivial group more generally when we discuss subgroups. But very quickly, let's verify that this is a group. 1 times 1 is 1, which is in the singleton set containing 1. So it is closed under multiplication. No matter how you multiply 1 with itself 3 times, you will obtain the same result. 1 is the identity under multiplication, and it is in the set. And 1 is its own multiplicative inverse. So this is a group. Okay, so next time we will look at the concept of a field and an affine space and continue to look at equations in these structures. So I hope you have enjoyed the 10th lecture. Thanks for watching.